on the different properties of electricity, and resistance was one of those main properties that we calculated. Well, in this video, we're going to get deeper into that idea of resistance and start talking about what properties comprise the resistance of a material. All conductors have some sort of resistance. Good conductors have a very low resistance, but there are a variety of different factors that affect how much resistance a conductor has. So let's start by talking about what are some of those factors that might affect it. Well, if you think of a wire, there's some different things that you can do to a wire to change how it operates in terms of the electricity that can flow through it. The first is by affecting its cross-sectional area, basically making the wire thicker or thinner. If you have a very heavy gauge extension cord, that's usually a very thick wire. It offers very low resistance overall, which can allow more current to flow through. A filament in a light bulb has a very thin cross-sectional area, which provides a lot of resistance. Another factor that you can change is the length. The longer your wire is, the more resistance it's going to have. And then the final factor is changing the material of the wire, what it's actually made out of, because different materials will offer different levels of resistance. So in this video, we're going to look at these three properties and why each of those affect the overall resistance of that conductor. The first thing that I want to look at is looking at how changing the shape of the wire changes its resistance. So to think of this in a physical sense, imagine that you're drinking a milkshake through a straw. Now, a milkshake is hard to drink through a straw already because the straw provides a certain amount of resistance to draw the milkshake through it. But if you lengthen that straw, it provides even more resistance. The longer the straw is, the more resistance it's going to provide for you trying to drink the milkshake through it. So we say that the resistance is proportional to, that's what this symbol means, the length of that straw. The longer the straw is, the more resistance it provides. Also, if we think of changing the shape of the straw, if we make a straw much wider, increase its cross-sectional area, you can imagine that it becomes easier to drink a straw or drink a milkshake through a fat straw than a tiny skinny straw. So we would say that the resistance is proportional to the inverse, 1 over the area, which means that if the area gets big, then the resistance has to go down and vice versa. So if we were to combine all of this into a mathematical relationship, the relationship looks something like this, where the length is directly proportional to the resistance and the area is inversely proportional to the resistance. So R, in this case, represents our resistance of the conductor. As we talked about before, resistance is measured in units of ohms. We represent that with an omega symbol. L is how we're going to represent the length of our wire. L for length, we're going to represent that in units that we've represented length thus far in meters. A is our cross-sectional area. So here in this picture, it's the circle that's shaded in purple. An area has to have units of area. That's a length squared, basically. So in this case, we're typically going to use meters squared. And if you were to calculate the area, if you were given the diameter or the radius, you need to use the equation to find the cross-sectional area. Most wires are going to be in a cylindrical format. So the cross-sectional area is by nature a circle. So pi r squared is typically going to be the equation that helps you get to the cross-sectional area of that. Now, you could also have a resistor or a wire that has a different shape cross-sectional area, like a square or a rectangle. And in that case, you would just calculate the area accordingly. But pi r squared is what we're going to use most often to get our units of meters squared. Now we have one last symbol here in this equation, and it kind of looks like a lowercase p, but it actually isn't a lowercase p. It's a Greek letter rho, R-H-O, Greek letter rho. And rho, in this case, is representing a property known as resistivity. This is where that material factors in. So the different materials that you can provide will offer different resistivity to the circuit overall. And our unit for resistivity could be calculated or determined based on just dimensional analysis of ohms, meters, and meters squared. What you'd be left with is ohm meters. So it's how many ohms for every meter of material it would provide. Okay. You could also, in this case, swap out meters for another length measurement as long as you were consistent and did it in all regards. So you could have a length in centimeters, area in centimeters squared, and a resistivity in centimeter or ohm centimeters. Either would be fine. This equation is given to you in the data booklet. It's just in a slightly different format. Instead of solving it for resistance, it's rearranged to solve for rho. That resistivity value is just resistance times the area divided by the length. So whichever equation you use is fine. You can rearrange to solve for either. So let's look at this rho, this resistivity value. Resistivity changes depending on the material that's used. And in this table here, you can see a resistivity for a variety of different materials in ohm meters. It's provided at a temperature here. We'll see a little bit later on that temperature can change your resistivity. So in this case, I see silver has a resistivity of 1.64 times 10 to the minus 8th, whereas like iron is 12.0 times 10 to the minus 8th. The higher it is on this list, the lower your resistivity, the better conductor you have. Copper, as you can see, is a pretty low resistivity value. It doesn't offer a lot of resistance for its material, the amount of meters that you're using. So it makes a great conductor, something that we use a lot in electrical circuits and wires. Silver, gold are even better conductors, but they are much more expensive and don't give you as much bang for your buck. So looking at this table, it's going to help us provide enough information to calculate the resistance of the wire described here. So I would like to calculate the resistance of a 1.8 meter length of iron wire with a diameter of 3 millimeters. So this is going to offer some resistance to electricity flowing through it, and we can calculate that. In this case, 1.8 meters is the length of the wire, that's L. The iron conductor is providing a resistivity of 12.0 times 10 to the minus 8 ohm meters. And then the last piece is we need to calculate the area because we now know L and we know rho, but we don't know A. In this case, it's a wire with a diameter of 3 millimeters. I'm using meters, everything else, so I need to convert that into meters and then solve for its area. Well, area is pi r squared. So pi times the radius, which is 0.003 meters instead of millimeters, divided by 2, because this was the diameter. I have to divide by 2 to get to the radius and then square that. I get a really tiny area, but that makes sense in terms of square meters, that I've got about 7.07 times 10 to the minus 6 square meters as the area, cross-sectional area of this wire. Then I can take all of these values, plug it into this equation. I've got r is equal to 12 times 10 to the minus 8 times 1.8 divided by 7.07 times 10 to the minus 6, and go ahead and solve to find that resistance. Plugging that into my calculator, making sure that I use parentheses or the capital E key on my calculator, I should end up with a resistance of about 0.03 ohms. So very low resistance, which makes sense. You don't want wires that have a lot of resistance because the components are typically where the resistance comes from. The wires we typically in our analysis consider no resistance at all. It doesn't affect it that much, but it does affect it enough potentially if it's a long length of wire that it could slow down that current a little bit. Let's look at another example here. Using this equation the way it's written in the IB Physics data booklet, a current of 4 amps flowed through a 75 meter length of metal alloy wire of an area 2.4 millimeters squared when the potential difference of 12 volts was applied across the ends. What is the resistivity of the alloy? So in this case, we're trying to figure out what that material's resistivity property is. So what we're given here, if we're trying to solve for rho, we are given the length, 75 meters is the length. That's easy. We're given enough information to calculate A. In this case, A, the area, is given. It's given in 2.4 millimeters squared. I want to make sure that my units agree with each other, and I've got millimeters and meters, so I'm going to convert that to meters squared. It's not quite as simple as just moving the decimal 3 times because it's a squared quantity. So if you remember doing that dimensional analysis, you need to square your conversion factor to make the units agree. So it's basically 2.4 divided by 1,000 divided by 1,000 again. We end up with 2.4 times 10 to the minus 6th. We're moving that decimal 6 places. And then the last variable that we need is the resistance. We are not provided the resistance in ohms here. Instead, we are provided a current and a voltage. This current is 4 amps. The voltage is 12 volts. Ohm's law relates those two, that the resistance is just voltage divided by current, V over I. 12 divided by 4 is 3 ohms. So with all of that in mind, we can plug that into this equation. 3 times 2.4 times 10 to the minus 6 divided by 75 gives us a resistivity right in the same range as the other ones that we saw, that times 10 to the minus 8 magnitude. So 9.6 times 10 to the minus 8 ohm meters for the resistivity of that alloy. So for all of these resistors that we've talked about so far, we've assumed something. We've assumed that it always follows Ohm's law in a relationship that is linear. And what I mean by that is if we were to find the potential difference in the current flowing through a resistor and keep increasing the voltage, we're going to keep increasing the current, because the more voltage, the bigger the push, the more current comes out of that. So we see this increasing value, that the bigger the voltage, the bigger the current. Well, if you put in a different resistor in its place, you're not going to get exactly the same current for the same amount of voltage. Instead, you might get something that looks like this. Both of these are linear relationships, so we would call that component ohmic, because it follows Ohm's law in this linear fashion, and the resistance isn't changing. Within each of these, we can actually figure out, is this resistor a high resistance or a low resistance by looking at the slope. In this case, a high resistance is one that for a given voltage gives you less current. Basically, it doesn't flow as fast if you're pushing it at that constant amount. Low resistance gives you a higher current for that same amount of resistance. So in each of these, resistance is constant. We're just swapping out one resistor for the other, but it never changes its value when you give more current or more voltage. If we look further, there are some resistors that do not follow this linear relationship. Most electrical resistors are not perfectly ohmic. The most common things that we talk about, like light bulbs that are this incandescent filament, actually change the resistance as they heat up. So they actually have more resistance when they're hotter. The resistivity of the material increases, which flattens out this graph. We call these non-linear relationships non-ohmic, which kind of makes sense. We got ohmic is our linear, non-ohmic is our non-linear, these curved values. So you might see a graph that looks like this. In this case, X is our ohmic resistor and Y is our non-ohmic resistor. But that gives us enough information to actually calculate a couple different things from this value. If I want to find the values of these resistors at 2 amps, 2 amps is my current. But looking at resistor X here at 2 amps, I see I needed 4 volts in order to make that happen. So I see 4 volts here. That 4 volts, if I want to find the resistance is just 4, or the voltage divided by the current. 4 volts divided by 2 amps will give me 2 ohms of resistance. If I want to do the same 2 amps of current for resistor Y, 10 volts are required. Same thing here, resistance is just voltage divided by current. 10 divided by 2 is 5 ohms of resistance there. If I were to test different values for X, I would always get 2 ohms. But if I checked different values for Y, since the slope is changing, my resistance is changing. It is non-ohmic. So from this lesson, you should be able to describe the different factors that affect resistance, that resistivity equation, like length, area, and resistivity of the material. I can define the resistivity as a property of that material. and talk about, is a high resistivity a better conductor or a worse conductor? And then compare ohmic versus non-ohmic resistors. Which one is linear and why does that matter for us in the long run?